Hello. In this lecture, we are going to focus on performance metrics regarding the classification models. So I'm importing this tidyverse library and I'm reading in the AutoMPG clean dataset, which is the same as AutoMPG, but without any missing values. So let's check this data now. So as you can see, there's some information on vehicles regarding different attributes. And there's the car name. So the first thing I will do is I will get rid of the car name because we're not going to use that. Okay. So I will say F. And then I'll say, okay, select minus the car name because we don't want that anymore. And then I'm going to also do a few changes to my dataset. So I will change the model year and the origin into categorical variables. Right now, as you can see, they are numeric because the minimum, maximum, mean, median, and different statistics are computed. So it's numeric basically, right? So I don't want them to be numeric because origin is basically the country that the car is coming from, and model year again. It's referring to the year, so it's not actually a numeric value. It's more of a categorical value there. So I will say mutate, and then I will use the same names, and basically I will overwrite them. So I will say model year, and then factor model year. Okay. So let me put this on the next line here. And then I will say origin is equal to factor origin. Okay. If I do this, let's quickly run it. Okay, it looks to be fine. Let's save this back into the df name, df variable, and let's check whether we have done it correctly. So I don't see the car name anymore, and model year and origin are factor variables. Okay, so good. So now the next step I will do is basically I want to convert the MPG column, the MPG variable, from numeric into a categorical value of two values, low and high, meaning low miles per gallon and high miles per gallon. So for that, I will make use of the cut variable, cut function. So that's cut, and then I will give the name of the variable that I want to discretize. That's the MPG column that will be discretized here. And then if you say brakes is equal to 2, so I want to basically have two levels, right, low and high, so that's why. So if I just say this, if I run this, okay, so I'm getting what I want. So let's save this back into our data frame. I will call this discrete, and I will name this 1. Okay. And the next thing I will do is I'll use the same function, and I will do just a small thing different here. So here, brakes, if you just give it a number, so it will create 2 brakes. It will basically create 2 bins, okay? But the value that it chooses, I think it goes with like the mean value or something like that. But if you want to exactly specify the cut lines yourself, so that you know exactly what's going on, you can do that. So you can do that in this way. So this 0 and 100 are just arbitrary numbers, actually, just to cover all, everything possible in the dataset. The 25 is my threshold here. So if I use this function now, I will know that anything below 25 will be low, anything above 25 will be high. Okay, so let's do that, and okay, let's save this. This is MPG discrete 2. Okay, so now if I check, so if I actually let's go here. But if you check here, so everything is low, 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 low. Okay, so here it becomes high. So let's wait. I think I did not save MPG discrete 1. Okay, so let's recheck it. Okay, So okay, for example here, MPG discrete 2 is high and MPG discrete 1 is low. Why? So let's look at the actual MPG value. It's 27. And in MPG discrete 2, I use 25 as threshold, right? So that's why 27 is high if I use 25 as a threshold. But in MPG discrete 1, it's low. And since if you want to see, okay, what kind of a threshold it used, so we can just do this. Let's do it here. So if I don't specify the labels, it will show the whole vector with the bins it's using for. Okay. So here the first bin is any car that has miles per gallon between 8.96 and 27.8. And next bin is 27.8 up until 46.6. So what this 46.6 is that's the maximum MPG value, 8.96 is the lowest MPG value in the dataset, and 27.8 is its threshold basically. Okay. So we can see that from the summary. Yeah, you've seen miles per gallon. So it's so it takes 46.6. Okay, so yeah, this is the maximum value as you see. The 8.96 here it's 9. So this is I think just like a rounded number here. But basically those are not important. The middle value is the important one because this is the threshold. Okay. But as I said, if you want to specify the threshold yourself and to know it exactly, you can do that with this one. So that's what we'll do. We'll run with the second value here. Okay. So there's one more way to create this bin, and that's using the mutate function. So we can say mutate, and then I will give the dataset name, and then I will say MPG discrete p, for example. Okay, and then is equal to. So I will use this if else, and then I will check the MPG column. Condition will be here. I will again set 25 as my threshold. And then if it is above 25, it will assign H, high miles per gallon. So this is the condition here. This is if that condition is true. And next I will assign the value if the condition is false and that I want to be low. Okay, so if I just run this, see it's giving those values. So let's save this back just like before, so that we can compare them all together. So now again, if you go to df here, so this is the last one that I created, MPG discrete 3, using the mutate function. So if you scroll down, it should agree with MPG discrete 2, everything should be the same. Okay, so it doesn't agree with discrete 1 because there the threshold is different. Okay, I guess you get it now for how to create this discrete bins. Basically, we're converting a continuous value into a categorical value. Okay, so now we'll choose one, drop the other ones, and then continue from there. So what I will do is I will say df select. I want to select this last one is the same as the MPG discrete one. I will just go with this, doesn't matter. I want to select that one, and I want to drop the other one. So let's see if this works fine. So I want to drop MPG, I want to drop MPG discrete 2, and I want to drop MPG discrete 1. I don't know what happened there. Okay, discrete 1, and the first one should be MPG here. I don't want to keep that continuous value anymore. Okay, so if you run this, okay, so I think it worked fine. Let's save it here, and then check back our data frame here. Oh no, okay, right here I said okay, select this one, and then it just you can't do this like this. So let's delete this. Let's go back from the beginning. I will quickly run it again. Okay, so I have dropped those columns, right? So if I check now, okay, I'll go back here. Okay, so I have all the attributes and then MPG discrete 3. Okay, so now we're good. However, I don't want to keep this name as is like this. I want to change that. So if you want to change a column name in R using the library, you can use the rename function. Okay, so I will say rename, and then give the dataset name, df, and then I will say, okay, rename the new value I want to see is MPG discrete. Okay, the old one you write here. So you write MPG discrete is equal to MPG discrete 3. Okay, so let's save this back into the df variable. Check here whether we have changed it. Yes, we have. We are good now. So we have attributes as origin, model year, acceleration, weight, horsepower, displacement, and cylinders. Okay. And MPG discrete is my target variable, is the one that I will use as my label for my data set. Okay, we want to predict this one. Okay, so now our data is ready. So the next step we need to do is train test split. Okay, we got the train test split now. So how can we do the train test split? So for this, there is like several models, several methods you can really use. The one I will use is from the Caret library. So I will say the library Caret, so that loads up. So you can also check your libraries here whether you can, whether they are loaded. So if I go up, you can see that Caret has a tick next to it, so it's loaded now. Okay. Okay. So we have that. So within the Caret library, there's a function called create a partition. All right. So I will say, so the first thing you should give is variable that you want to split on your data on, your target variable basically. So it's called the MPG discrete here, right? So what this will do is we will assign it, let's say equals 0.7, which means 70% of your data you want to go one side and 30% will go to the other side. And the 70% will constitute our training set, the 30% will constitute the testing set, all right? So, and make list equals false. If I just run this now, so you will get a, like so, it shows the indices, the row indices, okay? So let's save this into sample. And what this does, by the way, is it does stratified sampling. So what that means is that it preserves the percentages of the low miles per gallon and high miles per gallon in each set. Okay, so what that means is that if there was, let's say, only 10% low miles per gallon vehicles and 90% high miles per gallon vehicles, after the split is done, in each, in the training set and the testing set, there will still be approximately 10% low miles per gallon and 90% high miles per gallon vehicles. Okay, it won't be exact, but it will be almost the same. Okay, so we have that now. In order to create the training and test set, we will say train is equal to df and then sample, comma. We will repeat the same thing for testing set. So we will say test is equal to df sample, but this time minus sample. Okay, so if you do this and this, so now let's check str train. So you can see there's 279 observations. str test has 119 observations. Okay. So let's check another thing here. So let me try this. So I will say table, okay, df, and then mpg discrete. Okay, so there's high and low values. So I think after that there was this function here. Okay, so after you create a table like this here, if you put that into the prop table function, it will show the proportion of the high and low miles per gallon vehicles. So this is for DF, okay, so the main data set. So let's check whether this is indeed preserved in both the training and testing sets. This, I mean this proportion. As I said, after the split is done, the proportion should be preserved. Okay, so this is the training set proportions of low and high miles per gallon vehicles. So as I said, it won't be like 100% the same, but it will be very, very close, because at the end there will be a few points off here and there. Okay, so that's fine. And this is the testing set proportion. So you see that it's okay. I mean, the proportions are preserved. Okay, so let me write that here. Proportions of the target variable values are preserved after the split. So this is called stratified sampling. Stratified. All right. Okay, so so we got that. So now we have your training set. We will use that to train our model. And then after that, we are going to test our model on the testing set. All right. Okay, so let's do that. So we will build a decision tree. Okay, so for that we will use the library rpart. Okay, so I will call the decision tree decision1 or deck1, and then the function is rpart, and then I want to, my target variable is the mpg discrete. Okay. And I want to use, let's say, everything I have in my data set. In my data, so be careful here, you should say train, do not use the df, the main data frame anymore. It's a train data set that we will work on to build our models. If I save this, I run this, and then, so let's actually let's also import this rattle library. This is a good visualization library to visualize how the tree looks like. Okay. So this is our tree here. Okay. So the first split it uses, for example, is cylinders. What this shows is that cylinders is the most important variable. So it asks the question, okay, is the cylinders value less than 5.5? So by the way, we kept cylinders as numeric because there's an order there. So I didn't want to touch it. I still could have converted it into a factor variable. At the end, it's a bit your choice here. So you can choose the way you want to. As long as it makes sense, that should be okay. You can also just apply different models by using both cylinders as numeric, or in the other model you can use it when you convert it, after you convert it to categorical type, and then you can compare the accuracies, and then you can go with the model with the type that gives you better accuracy. If it changes at all, I don't know if this will affect anything, but it could, so you can try it. So anyway, so here the question is the cylinders less than 5.5? If yes, it goes here. If no, it goes here. So if no, if any car has more cylinders than this, then basically it's a low miles per gallon vehicle. And what these values show here is, here for example 47%. So this 47% means overall this node contains 47% of the data points, okay, in the training set. So here, for example, it starts with 100%, right? Everything at the first node, everything is there, so it's 100%. And the proportion is 40% of these vehicles is low and 60% is high. Or wait, is it the other way around? So let me check these proportions again. Okay, 40% is high, 60% is low, sorry. So 40%, you can see here 40% is high, 60% is low. And yeah, so you can actually see that from the color as well. When it is high, it uses the green color. The more, the higher it becomes, the darker green it becomes. The more lower it becomes, the darker blue it becomes. So here, it's actually blue. So 60% is blue out of the total vehicles. 40% is high. Okay. So yeah, so this branch is easy. Okay, so the split is done, and this is the final node here, so the leaf node. Okay. So any car that has more than 5.5 cylinders falls into the low miles per gallon category with 96% probability. So then here, if you go to the left, these are the vehicles which have less than 5.5 cylinders. The first one here is categorized as high miles per gallon with 71% probability. Okay, 0.71 probability. But then it continues to make more splits on this. And the next question it's asking is about model year of the vehicle. So if it falls into these model years, yes, it goes to this branch. No, so meaning any other year the vehicle was built in, it goes here. So in this case, 72, 73, 75, 76, and so on will go to this branch, and so on. So these are the leaf nodes at the end. Okay. Okay. So that's how our tree looks like. Now let's make predictions on this tree. So we will give the model name. We will give the new data name. So the new data will be test, right? That's what we want to test on. Okay, we don't want to test on the same train set, because if you do that, then we will have a more optimistic result, which will be misleading, misguiding. But we don't want to do that. So the new data is test. That's here. Okay. So then there is one more thing that we need to specify, and that's a type. So if you say type is equal to prob, what this will give is the probability of each class being predicted. Okay, you can see here on the bottom, the first column is the probability of this row, of this point, point 2, being predicted as high miles per gallon, and the second column is this row, or this point 2, being classified as low miles per gallon vehicle. And here it's pretty sure that this is a low miles per gallon, because the probability of low is 0.96. The high is very, very small, it's 0.03. Okay. So these are the probabilities of each class being predicted for each point. Now, if you want to directly get the class variable being predicted, you can say type class, then it will directly show, okay, the first point I predicted as low, the second point, or 0.3 by index, this is the index of the point, is low, and so on. So by the way, these indices, as you can see, for example, here it goes 2, 3, 11. Remember, we made the train test split. So this is the very original row index value. So in the original data frame, this point was like row 2, this was on row 3, this was on row 11, and so on. So those numbers come from the original data frame. Okay. But that doesn't affect anything. So at the end, it just shows that index that comes from the DF, the original data frame. Okay. So okay, so we got that. So let's save this prediction into pred. Now let's calculate the accuracy. So the accuracy is, okay, how was the model able to predict a low miles per gallon vehicle or the high miles per gallon vehicle? What was the accuracy on that? So for that we will say, okay, the actual is this one, miles per gallon discrete. Then I'll say equal to pred. So this will show, it will basically create a true false vector like this. So when they are equal, it will be true. When they are not, it will be false. And those falses basically mean my errors, right? So I was not able to predict correctly here. So then if I if I just take the mean of this, so the mean, remember the true and false values are treated as 1 and 0s. So true is 1 and false is 0. In coding in many languages, it's like that. So in R, it's the same thing. So then if you just take the mean of this, so it will directly convert this true-false vector, which is a Boolean vector, which is a logical vector, into like a numeric type to basically 1 and 0s. And then it will calculate the mean. Basically, that will show you the accuracy. Okay. So my accuracy is 0.87. So if you just multiply this by 100, that means 87% accuracy, which is pretty good. Not bad. Okay, so we got that there. Now, the same regard, so here let's write this list. So here we're calculating accuracy, and let's say we want to calculate the error. Well, it's just like instead of using equally here, I can just say, okay, not equal to, and this will show 12.60. Basically, it's my error percentage. Okay, so like 13% error in my model. All right. So accuracy or the error. So this is maybe the better naming for this would be misclassification. Okay, because it's bad classification, right? So so we are misclassifying here. Okay, so either way, either you go with accuracy or misclassification. This is like a very broad performance metric. Okay, this will not show exactly how your model is doing. Especially if you have an unbalanced data, meaning you have a lot more points from one class compared to the other. In those kind of situations, using just the accuracy won't tell you the whole story. So, for example, if you were to have, I don't know, out of 100 points, let's say you have a small data set, 100 points, 90 are from one class 1, and only 10 are from class 2. Well, if my model were a very basic model, okay, I would just predict everything to be from class 1 because that's the majority, and I would get 90% accuracy, right there, without doing anything. So I just look at the number of points from each class, and then I just choose the one that has more points, and I say, okay, this is my model. I will always predict this class. So that's your base model, by the way, in classification. Okay, so base model is the one that has more points. So the majority class, basically. So, but you can see that even if you build a model after that, no matter what kind of model you build, actually it will have quite a bit difficulty reaching that 90% accuracy. So many models actually will just say, okay, they will also choose that, choose to predict everything from the majority class. And if you just calculate accuracy, you will be happy with your result, but actually your model is not really doing anything. Okay, so what can we do about that to see a better result? So we can check this, okay? So remember this test MPG. Let's check that. Test MPG screen. So this is a low miles per gallon, high miles per gallon vehicle. This is a vector, and we are predicting the similar vector like this, low and high. So basically, what I can do is I can create a table, right? This and then pick the results. So if I say pred here and the test MPG here, okay. So you see, this is what we call a confusion matrix. Okay. So what this shows is this. So here on the rows you have the predictions. On the columns you have the actual values, the truth values. So for example, what this shows is HH means 40 vehicles. So these are the correct predictions because I predict H, actual class is H, so we are good here. Low, the same thing. So this diagonal elements here are the correct ones. So these are the low miles per gallon vehicles. The model predicted them to be low, so these are good. The errors are these ones. Okay, so what this means is this. There were 8 vehicles which have low miles per gallon, so these are the actual values here, the columns. But the model predicted them to be high miles per gallon. Okay, that's here. When you look here, okay, so it says, okay, so there was 7 high miles per gallon vehicles, but the model predicted them to be low miles per gallon vehicles. Okay, so these two are the errors. Okay, so now, for example, by just looking at these values here, so let me do this. I copy paste that here, and I will comment them out. Okay. Now from this table, we can calculate still the accuracy that we saw above. Okay, so you can see we can say 40 plus 64 divide by basically everything. Okay, so I can just add them up one by one here. Plus 7 plus 64. If I just run this, so you see I get 87.39 accuracy, and that was the same as before. So that's the accuracy there. But you see now we can see more. And now we can see how that breaks down, that classification, the model, that how it breaks down in different among the different values of our target variable, right? Now this tells a better story. Okay, this tells a much better story. Okay, so there is a function called confusion matrix in the caret library that actually creates this table for us and also calculates the other metrics. So let's do that now. So let's give the values here. So so before we can use this, we will create a prediction data frame. Okay, so I will call this dfpred. Okay, I will say data.frame, and then I'll give the prediction we just got, and then also the actual miles per gallon value. So once you have this, so let's check how that looks like here with just 2 columns, prediction and miles per gallon discrete. And then what I will do is, so I will say if pred, okay. And then from the same data frame, miles per gallon discrete, and then also specify a positive class here. Once you create okay, I think there are some other functions called confusion matrix from other libraries. So if you get an error that I just got there, you need to specify from which library the function you want to use. Okay, so in this case I want to use from the caret library, and I put this colon, okay, just 2 colons next to each other. Once you do that, it will just read from this library. Okay, this function will directly come from this library. So this also prevents any confusion. But yeah, so this function will create these results here. So this is the table that I just showed you, the confusion matrix. So it creates that. And based on this table, it also calculates many different matrices here. So the accuracy is here. So for example, there's the value called sensitivity, specificity, like balanced accuracy, and so on. So these are all important metrics, okay? And I will explain them soon to you. So, but this, so these are important metrics to assess like how your model is performing, basically. All right. So let's do this. So let's go here. So now, after showing you all that, I will explain you what those were. Okay. So I'm a bit of going in the reverse order here. Okay, so the performance metrics. So today we're going to learn about this train test split and the different metrics regarding performance. The train test split, okay, I just explained why we are doing that. But basically the idea is so that you'll train on one set and test on an unseen data set. Okay, the general preferred values is 80-20% split or the 70-30% split. You can try other values as well. This is not really super important, but just make sure that you have enough points in your test set. I don't know, so like to start with, there shouldn't be, assuming there's like some 1,000 points. So a 20% split would give you like 200 points. That's good enough. So anything below 100 points in test set can be problematic, because if you have too little, not enough points, then even though you're assessing on an unseen data set, you'll still can't really understand how good or bad your model is doing, because there's just not enough points to basically cover that space, okay, of the variance in your data. So there should be enough points. Okay. So I would say at least somewhere around like 100 points in your test set is good enough. So here, for example, we have a sample small data set. Okay, we split by using 80-20 split, so 80% goes in the train and 20% goes in the validation portion. So validation, some resources call it the validation set, some call it the test set. It's okay to use both. So that's being shown here. So the R-squared metric is used in regression, right? So this is how it's calculated. So SS total, this means the sum of squares in your base model, which means by using only the mean model, okay, the mean value, that's here. The SS residual is the sum of squared of the residuals or the fitted model. Basically, it's the difference between the actual value and the predicted value. And then 1 minus SS residual divided by SS total will give you R squared. And this is a common metric used in regression. Another very common one is the RMSE. So it stands for root mean square error metric. It's the difference between the actual value and the prediction. The square of that, you sum them up, you take the mean, and then you take the square root of that final value. So that's the RMSE there. So for classification, you can use accuracy, and this is how it's calculated. It's basically comparing your prediction with the actual class and see whether they are, correspond to each other or not, whether they match each other or not. If you just go the other way, you can calculate them as classification rate or 0-1 loss, which is also the same name, another name used for this metric. Okay, instead of being equal, you compare whether they are not equal. So when they are not equal, that's a misclassification, right? Okay, so let's come to the main portion here. So the confusion matrix. Okay. So sometimes on the rows, you will see that the predictions are being used. Sometimes the actual being used. It really depends on the package, on the way they adopt it. So here I'm using the rows being actual and the columns being predictions. Okay. So here, if that's the case, so if my actuals are on the rows and the predictions are on the columns, so when both agree with each other, the negative class agree with each other, this is called true negative. When positive class agree with each other, it's called a true positive. When you predict as positive, but in actual it is a negative class here, so this place here, that's a false positive, right? So it was actually negative, but the model is predicting positive, so that's called false positive. When the model is predicting negative value here, but in reality it's a positive class, so that's a false negative, right? So you're saying it's negative, so the model is saying it's negative, but in actual it's positive, so that's false negative there. Okay. So the formulas for the precision and recall are being shown here. So recall, okay, is also called sensitivity. What that means is that out of the total number of positive points in your dataset, how many is the model able to find correctly? So you see it says true positive and false negative here. So if you go here, true positive and false negative. So that's actual plus 1. Okay, so actual plus 1. Actual plus 1 So that's all the actual positive values. And these are your true positive, meaning out of those actual true positive values, how many is the model able to find correctly, okay? And that's here. So that's recall. It's also called sensitivity, okay? They are the same thing. Precision is this. So in precision, out of the model's predictions of positive values, how many of them are correct? So you see true positive, false positive. So if you go back here, true positive here, false positive is here. So that's this place here. So predicted positive class. Okay, predicted positive class. Out of your predicted positive values, how many of them are actually true positive? Okay. Precision is how many out of your how many of your past predictions are actually true positive. And recall means out of the actual positive cases, how many is the model able to find? Okay, how many of them is it how many is it able to find correctly? True positive here. Okay, so these are the two important metrics, and out of these two, another important metric is being calculated, and that's called the F1 score. That's calculated as 2 times precision times recall divided by precision plus recall. So by using these two values, F1 score is calculated. And overall, F1 score is a much better metric compared to the accuracy. So instead of using accuracy to compare different models, F1 score is the preferred one to go with. Okay, and those are shown here. So recall is calculated by using this row here. And precision is calculated by using this column here. Okay. Okay, so an example here. So you got the table, a confusion matrix like this. So these are the labels, the true negative, false negative, and true positive labels. And these are how these metrics are calculated. Okay, so you got the accuracy, you got the error, you got the precision recall, and the F1 score here are all shown. Okay, so once we have those in place, we can calculate these metrics from this confusion matrix here. Okay, so there's 30 true negative values, 50 true positive, 15 false positive, and 5 false negative values. Once you have these values, you can just plug them into these formulas, and then you get the results. So for the accuracy, you just have this true negative, true positive values. You add them up and you divide it by the total number of points in your data set. So 80% accuracy. So 1 minus that will give you the error. So 20% error you have in this prediction. Precision. So precision is here. Okay. So out of your past predictions, how many of them are correct? So there's 65 in total. Past predictions, 50 of them are correct. So 50 divided by 65, which gives you 0.77, is your precision. Recall is out of the true positive class, this one, this row here. How many of them are correctly classified? So 55, okay, out of the 55 points, 50 are found correctly. So 50 divided by 55 gives you 0.91. F1 is 2 times precision times recall divided by 0.77 plus 0.91. That gives you 0.83 F1 score. So here in this exercise, at least, F1 score is pretty close to accuracy. But as I said, overall, it's better to report the F1 score rather than the accuracy on your model performance. So here is another example. Calculations are not shown. Okay. Basically, if you were to take these numbers and apply the same formula, you will get these results. You should get these results here. Okay. So here what I try to show is basically this is a more of a balanced set, right? I mean, there's like 55 from the positive class, right? So actual positive class, and 30 plus 15, 45 from the negative class. So the values are pretty close. So that's why you can see that accuracy, precision, recall, F1 score, they are not too far off from each other. Okay. when you have an unbalanced data set like here, so you have 83 plus 5, 88 points from the negative class and 12 points, only 12 points from the positive class. Okay, and your predictions are look like this, then basically you will have a very high accuracy, right? You have this 83 true negative and 2 true positive values that constitutes your accuracy, which is 0.85. So your model seems to be doing pretty good. But the problem is most of the points are from the negative class. And when that's the case, basically your precision and recall are suffering here. Why? Because it's not doing a good job in predicting this positive class. You see, out of this positive class, it's only, there's 12 points. The model is only able to find 2 of them correctly. 10 are false negative, so 10 are misclassified as negative. So that's a big problem. That's why the precision recall came out to be so low, and that also leads to a small F1 score value, right? But you couldn't see that in accuracy. Accuracy seemed to be very well, actually. All right, so yeah, that's the whole story of F1 score, precision, and recall. So again, if we go back to our session here, so right now you can see these values will make more sense. So you got the accuracy here, you got the sensitivity. So sensitivity also means recall, all right? And so this one doesn't show the F1 score, but you can calculate it yourself from this table. Okay. So actually for that, let's try this. So there's another library called Yardstick. So let's quickly check that as well. There you can calculate these metrics again, the performance metrics. Okay. So let's see. So in order to calculate sensitivity, the function name is called sense. And then the way it works is, well, actually, let's start with the confusion matrix from this library. So the confusion matrix is called confmat. Okay. What you do is you say estimate is equal to pred. The truth is equal to so the truth is equal to MPG discrete, and the dataset name is the dfpred dataset name that we just created. So let's try this. Okay, so you got the confusion matrix there. Okay. Sensitivity, so as input you give the same things here. Okay, so actually let's put the data frame as that begin. Okay, so we got the confusion matrix there. We got the sensitivity here. So this is the precision. Okay. So the F score is, the function for F score is F measure here. So this is the F measure. It's the F score, basically it's the F1 score, okay? It's 0.842. Okay. So yeah, so you can calculate these here as well from the library called Yardstick. Okay. Okay, so what else? So again, so this table actually is should be, you know, this confusion matrix table that provides these scores. So this balanced accuracy is also taking into account the like the class imbalance kind of. And actually, if this value is the average of sensitivity and specificity, okay, so this also will do a quite good job. So you don't have to always calculate the F1 score. So this one will also be, you know, equivalent to the F1 score. It's the average of the sensitivity and the specificity value. And this will also be a good measure to compare different models. Okay. So now, yeah, so let's say you had another decision tree. Okay. So let's go back here. So we used here everything in this first model. So I think that will be pretty good already. But let's say here you want to try another model where you use only, let's say, cylinders and maybe the weight of the vehicle. Okay, and maybe plus the displacement. Okay, so let's check the plot of this. Okay, so wow, actually it's doing quite a lot of splits here. So it uses the cylinders, the weight, again the weight, and then the displacement, and then the weight, and then the weight again. So it uses weight several times based on the different thresholds it's using, right? Okay, so let's now check the accuracy of this. So for that we will do prediction, right? We will say prediction, my model is decision 2, new data is test data, and then the type I want it to predict is class. So that's my prediction there. So now I will save this as prediction 2. And remember I had this data frame, dfpred. Okay. So now I will say dfpred, and then pred2 is this prediction here. Okay. So now I can compute all these different matrix. So instead of pred, I will use pred2, and then I will run the same confusion matrix function from the caret package. And once I do that, let's see. So did it improve? So accuracy, I think it decreased a bit. So the balance accuracy actually increased. Okay. Sensitivity also increased. So these are all good things. So interestingly, actually, balance accuracy. So let's put them on top of each other. Okay. So the first one, yeah, sensitivity was 0.85. So sensitivity increased, but the specificity decreased. Balance accuracy 0.87. So balance accuracy increased. The accuracy was 87. Accuracy decreased a bit. So actually, these two models are almost, you know, are very close to each other. So from this table as well, you can see that. I think this one is still better because you see it's I don't know, like these values are higher, and so this off-diagonal value should be lower. These values HH and LL should be high. So when I just look at this confusion matrix, I think the previous model is better. Why? Because it's also using more information, right? It was using all the variables there. So yeah, so basically this is how I make the comparison. And so actually let's calculate the F measure for both of these and compare them in that regard as well. So the first model which uses everything, like this one. has a F1 score of 0.842, and the second one has, interestingly, 0.846. So the second model, which uses less information with less variables, is doing a tiny bit better. Okay, and actually that might reveal the that might be actually important. Why? Because maybe in the model which uses all the variables is maybe kind of overfitting, and there might be some redundant variables who have almost the same kind of information. So whatever. So right now I'm not thinking about that, but basically I'm trying to show you how you should compare the different models. Okay. All right, guys. So so there is actually one more thing. So these measures that you by using the yardstick library, these sensitivity, precision, and so on. So you can combine them. So there's a function within the same library called matrix set. Okay, and then you can provide the different performance metrics that you want it to calculate for you, and then put together in a data frame format. So let's say I want to see accuracy, I want to see balance accuracy, okay. I want to see sensitivity, the specificity, okay. I want to see precision, and I want to see the F measure. Okay, so if I save this into a variable, so let's call this performance. Now if I run this performance, so this will be a function itself now, and basically what it does, it will basically call all these performance metrics one by one. Okay, so I will say performance, and then as input, okay, I will just give the same as here. If I do that, so the df_pred is my the prediction data frame that I created. Estimation is pred, and then truth is MPG discrete. So let's run this. So you see all these measures are being shown together in a nice way. So we can repeat the same thing for the other one. So let's call this performance matrix for decision tree model 1. Okay. And then the second one is the one for the second decision tree model. So I will call this pred2 here. If you run it, so you can see so here you have the first one, here bottom you have the second one. So the accuracy decreased, so this one increased a bit, so this one increased quite a bit. So the F measure increased also. So again, you don't like sensitivity, specificity are all important to check, but when comparing different models, you can just use either the balanced accuracy or the F measure to compare them. So in this case, if I had to just choose one, I guess I will choose the second one because the F measure has increased a bit. Okay, so yeah, so that's basically how this is done. Okay, so that's it. So in the future, when we add a few more classification models, then we will have a better understanding of how to compare them. But basically, so this comparison can be made by just using the same model by using the different creations of the model. Okay, so in this case, we just use the decision tree, but different models of the decision tree. You can also add, I don't know, KNN, k-nearest neighbors, or naive Bayes, or whatever, all the different models to make this comparison between the different models. Again, we will use these different performance matrices here. Okay, So okay, so thank you. That's it for today, and see you next time. Bye bye.